Witam wszystkich na pierwszym inauguracyjnym webinarze z serii cyklicznych webinarów, które będziemy prowadzić cały rok, co miesiąc o nowym temacie. Wiedza ma warstwy. Na początku też przypomnę, że webinar będzie prowadzony w języku angielskim. Proszę wszystkich o wyciszenie mikrofonów. Jakby podczas prezentacji, wystąpienia pojawiły się jakieś pytania, to proszę zadawać je na czacie. Ja je wszystkie zbiorę, będę nimi moderować i zadam na koniec naszym prelegentom. Też dodam, że już przygotowują się webinary na następny miesiąc. Zapowiadają się bardzo ciekawie, także zapraszam do obserwacji naszej strony warstwy. Link podeślę już na końcu prezentacji. I cóż, zaczynamy. So, okay, I want to welcome Niklas and Marcus from Xolo, and I will not talk a lot, so please, welcome.
Yeah, thank you very much, Anna. I didn't understand any word you said in Polish, but thank you for the kind introduction. My name is Niklas König. I'm leading the materials development in our company, Xolo. And I'm also responsible for following like use case development and business development. And together with Marcus, who is sitting behind me, he's our 3D printing specialist. We will guide you today through this webinar, and we would like to tell you about the background of xolography, but also show you how it looks like in practice. And this is when Marcus will come into play later. Our company is now 2 years old, so we are still a startup in a startup status. It's just 1 year ago that we moved from a university cellar to these nice offices and lab spaces that we found. And since December last year, we went out of stealth mode. We published a very nice paper, in my opinion, in the Nature magazine about our technology. And since then, we started to go into the public and advertise our prototype and our technology. And this is actually what we want to do with you today as well. We would like to share everything about our technology, about xolography. And I think we should just get started by giving you some background information. I will start sharing my screen now. I hope that it will work nicely. Just have to get rid of this small thingy. Yeah, volumetric 3D printing, no time for layers is the title. And what are we gonna do today? Presentation is a bit slow.
Everything is working well.
Everything is working well. Yeah, this is the agenda. We will first talk about the theory of xolography, then we will give you a practical course here, how it looks like to use our technology. Then in the end, we will briefly talk about our vision, what we want to do during the next 2 years. And then there will be time for questions and answers. First. Doesn't work. Computer ist abgestürzt. Xolography is a novel volumetric printing technology, and you see it here in the movie on the right-hand side. Our CEO always says it's like anything out of nothing magic technology, but in the end, it's not nothing that we have in the volume. It's our photopolymer that we have And it's possible in volumetric printing to address every voxel, so every pixel in the volume separately, and cause the solidification of the object regarding to the input file that you put there. The key selling points are really that volumetric generally and xolography in particular is very fast. So we print with 1 centimeter per minute. The precision is really unmatched. It's between 10 and 50 microns. In the end, it's depending on the build room that we address. And it's a technology that allows you to print without layers, because you address these voxels separately and you're not printing in layers anymore. And it's possible, as there's no build platform involved, to print everything without any support structure. So in the post-processing of your object, you don't have to cut off support structures, you don't have to polish your object afterwards, it is just clean. As it is a continuous process, these surfaces you get are really smooth and nice. The novelty of our approach is, in the end, the photo initiator. And that's very interesting. It's a deep dive into photochemistry now, but it's so beautiful that we really have to show it, and it's just important to understand this technology. So this is the novel photo switch here. It's a huge molecule in the end, but what you see here, important, is this benzophenone motif you see here. And benzophenones, they can, when they absorb light, be in an excited triplet state and initiate radical polymerization. But to this benzophenone motif, we incorporated a photo switch. And this is this part here. It's a spiropyrin. And spiropyrin photo switches, they are known to go into an open form when they absorb light. Here you see on the left-hand side, in this absorption spectrum, in blue, we have the absorption of the spiropyrin closed photoinitiator, and it tails out at around 400 nanometers here. And when it absorbs light in this region, then it opens to this merocyanine form, the red form here on the upper right side on this page. And this open form has now a very large conjugated pi system, and that results in absorption in the visible. And this you can see here in the absorption spectrum by this pronounced vis band of this orange line here. So spiropyrins can be switched with a wavelength lambda 1 in the UV region to a merocyanine, but this merocyanine relaxes back thermally, and it does that quite quickly if you want. We can follow this process actually by tracing the concentration of merocyanine by tracing the absorption at 600 nanometers, and this is what we did here. We see that when you shine lambda 1, the first wavelength, on a solution of spiropyrin, then the concentration of the merocyanine goes up until a certain point where the photo reaction is as fast as the thermal back relaxation. So you have an equilibrium concentration. And then when you switch off the light, then only the thermal back relaxation takes place, and immediately the concentration goes down, and the half-life is just some seconds here. And that's very important. So it is possible at a certain point in the volume to have this merocyanine form, and as soon as you switch off the light, it won't be there anymore. Because in the end, you make this benzophenone moiety photochrome, so it can change the absorption band. And this is what we use in our technology, as only this merocyanine open form can absorb visible light. We use this property to selectively address in the volume this molecule with visible light to induce the radical polymerization. So only the ground state of the molecule is everywhere in the cuvette, and only when we shine in light with the first wavelength, we have some of this merocyanine, and only at the intersection with the second wavelength, we activate the initiation of the polymerization. And the way we employed this now to a working technology is to be seen here. We have a cuvette, and in this volume we have a transparent photopolymer. Then we constructed a light sheet with the first wavelength. It's λ1 here in blue. And this light sheet now defines a print zone in the end, where we have this latent state, the pre-active form of our photoinitiator. And orthogonal to it, we have a 2D projection, just from a conventional 4K projector, which is shining in visible light. And at the intersection of the 2D projection and the 1D light sheet, we initiate the polymerization. And now we are moving this light sheet with λ1 through the cuvette continuously and quite rapidly also. And in the end, what we do from the other side, we are playing a movie. And like this, we construct the volume we construct the object in a continuous way within the volume. And in the end, it's a bit similar to what you know from stereolithography. It's just turned around by 90 degrees. Because when you compare it to standard stereolithography, you also have a vat here in blue, turned by 90 degrees, and the printing zone is actually between the platform or the built object and the surface of the screen or the membrane. And between the object and the membrane, you would usually have the printing zone where you cure your photopolymer, then you lift the platform or the object again, let the resin float into the so-built cavity, and you dip it in again, cure your layer, dip it out of the volume again, and so on and so forth. And that's why you have a layered process for standard stereolithography, while in our case, we have a continuous movement of the printing zone through our photopolymer. And that's why we're actually that fast, because instead of letting the resin flow into the printing zone, we let the printing zone go through the resin. And yeah, that's basically the whole trick about it. And this enables us also to use highly viscous resins, because in standard stereolithography, you use low viscosity resins, because they always have to flow into this print zone. And sometimes people are even heating up their photopolymer to make it less viscous, to be able to float in reasonable time into this cavity. But to be frank with you, our technology also comes with one limitation, and that is our photopolymers have to be absolutely transparent, because it relies on the intersection of two light beams. And you could imagine that if we have a hidden absorbing species in the volume, then the intensity would deviate depending on the penetration depth. And this would result in different kinetics depending on the space coordinate where you are in. And this we would like to avoid, to have a homogeneous print. So our resins need to be transparent, while in standard stereolithography you can also have non-transparent photoresins, as the printing zone is so small and you just have to shine light through like 50 microns. With that said, we can already go to the practical implications of xolography. And for that, we will go, because it's such a fast process, we can actually go through everything within this webinar, from resin preparation through the whole print, the post-processing, and we will have within, let's say, 15-20 minutes, we will have the cured object in our hand. And during we go through the laboratory and through the whole protocol, we can still give you some more details. So let me just go out of this share mode. I will switch around the camera to follow Markus. Okay, here he is.
Okay, and now we make the resin preparation. And here we use a urethane metacrilat. It's here, it's 200 grams. And here is our photo initiator, solved as a co-initiator. It's here. Now we mix these both liquids. And here you can see the high viscosity of our resin. Okay. And now we put the beaker in the new device we have until 1 week. It's the speed mixer. It's a very nice tool. It mixes and degases the resin. Maybe you can see this here. It's just a beaker, and it's a spinning device. It rotates like a centrifuge. Counter-rotates the liquid. And this process makes the mixing and degassing so easy. And here we have a program that runs 6 minutes. And yeah. And now we can go to the cuvette. We have prepared this resin before, just to cool it down and use it. Here we have the cuvettes. We have different sizes of the cuvettes. Here's a 3 centimeter, and we also have 5 centimeter, 1 centimeter, and also the big 10 centimeter. But here's the prepared resin. Here's the urethane metacrilat and the photo initiator. Here we fill it in the cuvette.
Beautiful.
Okay. So now we open our printer. And here we can show you what we are doing. Okay. Here we have, here on the right you can see the laser diodes, left and right. These are high power, here. This is a high power laser diode 405. Here we have a rotating mirror to generate the line out of a point. This is a focus lens. And here it's a collimation lens. And in the middle you have the cuvette, and here it's the beamer. It's the second wavelength. Okay.
So here we have the light sheet that is spanning through the volume, and orthogonal to it we have the projector that is projecting the 2-dimensional image into the print zone.
Yeah. Okay, now it's getting a little bit darker because our projector is very high powerful. So we put in the camera into the printer so you can see the process live. Okay, now we will start to print. And now here's the Xolography starts. Yep. The red one is the excited state, you can see. And the beamer shines the video. And now the video plays, and you can see the white solidification. And these are at a speed of 100 microns per second. It's a very beautiful process. I hope you can see this in the video.
Maybe it's a bit difficult to really see where what is, but it is maybe possible to see something like a red curtain, which is the fluorescent of our active molecule in the light sheet. And then you see something that is a bit more whitish, that is the actually already solidified object behind this curtain, because the curtain is moving through the vat. And behind the curtain, or the UV sheet, we have the solidified object. Yeah. So it should be possible to follow this live now. And Markus, maybe we can talk during that time now about the material varieties that we can actually polymerize in here. You said that right now we are producing a very tough material with diurethane methacrylate, which is standard in stereolithography. But what else is possible?
These are the hard materials, and then we can also print the biomaterials like gelatinate acrylate and all these things. And also some flexible materials we can show you after the print. The printing time for this 3 cm is 4 minutes. And yeah, I mean, we have some flexibility on the material side. Yeah, we don't know what you expect there, but
in the end,
is very wide.
In the end, we found that we can basically polymerize any acrylate. So usually we take methacrylates to have less of a shrink, but for example, JAMA is acrylamides on a protein, but we can also polymerize pre-ceramic polymers that contain these acrylic groups to allow for access of ceramics after a sintering process. Actually we are quite open with materials here. You just need to keep in mind that it should be as viscous as possible and transparent.
But you also can suspend nanoparticles in there, and the range is very wide. So when you have some ideas, we are open for it. Okay.
And I think the print is already done.
Yeah, the print is done. So we take this out and go to the post-processing.
I will follow with the camera. Wait. So we had a filter around the camera because there was so much light in our printer.
Maybe we can see the object inside the cuvette. I think yes.
When I move the camera a bit, we see that there's a structure in there. Yep. We did not tell you what structure we were printing actually, but we will.
Okay.
Fokussiert nicht mehr. Fokussiert die nicht mehr.
Okay, we have a little bit focus problems here, but I think we can solve this.
Yeah, we are sharp again.
Okay.
So what are you doing now, Markus?
Now I'm pouring this out here in a beaker. You can
try to give you a close-up.
Yeah, it's hard to see because you can see a little bit orange there. And then I move this to isopropanol.
This is quite a standard procedure that you already know from other stereolithography approaches. where you have to wash your object
Yep.
after print.
You can see it's a little bit sticky, the resin, because it's high viscous. Later we make some process for this to warm it up, and
yeah, in the end, for industrial applications, we will for sure have an automatized process here.
okay, now it's in the isopropanol, and now I'm shaking this.
Standard washing step.
And here you can see the structure. It's not clean. We have to shake it a little bit more, but this structure is there. Shaking a little bit. When you want, you can see a test print from today. It's a very nice.
Whoop.
I hope you can see this.
This is actually what we have printed here, just from this morning, 1 hour before. It's a, now I don't know how to pronounce it, gyroidal structure. It's like a framework with a high surface and small volume. Like a mathematical object with a lot of symmetries. And hopefully, what Markus will isolate from there will look the same, right?
Yeah, a little bit smaller because the printing process needs 4 minutes of. We have shortened this a little bit, but here you can see the structure.
You can see it already. There it is. Yeah.
Okay, and then we have to put this in the oven for 20 minutes or whatever. And here you can see this. It came out of the liquid. It's very nice, and the surface looks good. It's hard to see on the camera, maybe. Okay, we have prepared some printings there. With the post-processing is done. It's on the other side, on the demo object.
Yeah, I'm gonna follow you.
And here we have some demo objects. Here you can see the transparency of this object and the nice surfaces. I hope you can see this.
Yes.
Okay. I mean, it's very transparent. Oops, this is dark.
Yeah.
Okay. So it's very transparent, and the holes are there, and the surface looks very good.
Du machst einfach zwischen deinen Kopf und die Kamera. Yeah. And it's actually the same material, and it's really tough. I mean,
you can
exactly. So
here we have some.
We prepared some other materials.
It's a flexible sample, and you can see you can press this together, and the shape is the same after you press this. And here we also printed the big cuboid. It's made from the same material. It's very flexible, but big. So we can also print objects in this size, and you can make some. It's hard to see here, but this is a microfluidic device, and we have some examples. This is the CT head. Maybe you know this from our publication.
What's so special about him?
It's the specialty is you can see the lungs inside there, and the nose, and it's all 3 channels.
Yeah.
This is the specialty, and we don't need to remove the support structures, so you have very, very nice surfaces here, and we hope that we can print lenses with this. Even, I mean, we have showed the pole lens before. It's the small lens that makes a line out of a point. This works. You can see this on our paper, and yeah, when you need some examples, just call us, and we can give you more examples.
Yeah. What about showing the prototype to the people?
Yeah.
Yeah.
This is the prototype you can buy when you want to. This is our tube. Here we have some lights essentially. It's the same principle as there, but we have folded some devices here. At the bottom is the beamer, and we have a light. I hope it's possible to see. There's a light engine there. This reflects by the mirrors. Here's the curved plane.
So the printing zone is between these two optical devices there?
And you have also the two diode lasers with high power, the rotating mirrors to generate the line. The focus lenses are much smaller here. And here is the coordination. And this is our prototype. It looks really nice, I think, and it's 50 by 50 by 50. Maybe the design changed a little bit, but this is the shape of this. It's a cube.
Yeah. Okay. Thank you, Markus. I will start or just share two other slides with you about our prototype and what's our plan here. So let me share the screen again.
Technical issues.
We're getting there. Oh no. Oh my God. Oh, was ist hier das Problem?
Oh. Our printer is faster than the presentation.
Yeah, that's for sure. I'm so sorry. This presentation is slow. Okay, so if the slides don't want to work, I will just tell you like this. So our plan right now in 2021 is actually to sell 20 of these xubes of our first prototype to some really good academic institutions. And what we want to do with that is actually to give a fully flexible system to researchers to have a tool in their hand to solve problems that they were not able to solve before. And in our opinion, this should boost creativity a lot. So what we're thinking of is that people, for example, we got a lot of demand from people that said, I want to print very small channels, so microfluidics, but I can't do this with standard lithography. Do you have a solution for us? And there we really have the solution because we can build a prototype that is very, very precise in its print. So it's really possible to print channels with 20 or even 10 microns diameter. We would like to do this like a very efficient collaboration in the end, because we know that there will be some issues because it's a completely new technology. No one has real experience with it. So we would like to give you some training on this device. And as soon as we have any new finding regarding photoinitiators, for example, there is still a lot of room for improvement. We believe that we can be faster, that we can be more precise, for example, that we can have better green states in the future, so that it's maybe not even curing after the print needed. So we would like to support you always with the best system that is available at that time. And then We are really looking forward to working together with researchers that have creative ideas that normal industry doesn't have, or that we don't have, because we are not deep into your fields, actually. So this is what we want to do. We want to develop new fields with xolography together. And in the end, it would be very nice also to support you by publishing very good papers, because this is good for researchers. This is good for our technology because it gives visibility. It shows that it can solve problems. It gives acceptance in the community. This is basically our goal. The long-term perspective, let's say above 2021, so afterwards, and maybe if there are some people from industry also following this presentation, we are currently also developing other business cases, really for industrial verticals. Yeah, for that, sometimes you need really strong partners. Here we are finally on the page that I wanted to show you for the vision of 2021. So this is what you have already heard from me. So we want to sell 20 XUPs to very good academic institutions. The best would be to have a widespread over different research fields. And I'm really sorry for this PowerPoint presentation. It's too slow. And what did I want to say? We really believe that it's quite easy during this period also to publish very high impact papers, because the technology is so new. So you will be the first one who is able in your field to publish on a volumetrically printed object or solution to your research field. And then I was already saying that we are looking into some industry verticals. So we're always open to any kind of collaboration. We're open to any model, actually. And some verticals that we identified are the dental market, prototyping, jewelry. That could be very interesting to print as fast as we are printing. Then jewelry also, and optics. There, these smooth surfaces are really interesting, in my opinion. And then for microfluidics and biological applications, the high precision is really something that is a standalone factor for us. And with that, I finally want to close this presentation, and I hope that you have some questions that we could hopefully also answer. So thank you very much for your attention, and sorry again that the PowerPoint was a bit slow.
Okay, thank you guys so much. We have the question already. Maybe I will read it out loud so everybody also hear it. So it's from Jacek from University College Dublin. Hi, Niklas and Marcus. Great presentation and beautiful chemistry. Thank you for showing it. One thing, the printing is bound to the new crosslinker alone. Do you know how the biocompatibility of biomaterials printed with it compares to traditional Ergocure or HMPP photo crosslink gel? Maybe you can see the question in the chat. You can open it.
Yeah, I see it. So actually, we didn't do biocompatibility tests yet. So, but we are already working together with partners who are developing, for example, GELMA that is approved for medical use. And then we add our photoinitiator complex. And this is the difference to materials that are already on the market, right? And to be frank with you, we don't have cytotoxicological data on our initiating complex yet. But what we can tell you is that we are putting our photoinitiator in a very low concentration in there at around 100 micromolar. So I hope that this already reduces some of the risks. And in the end, yeah, we have to do these tests and they are not performed yet. And maybe we even find a partner who would do that for us. Because this is really a vertical that we will follow, and it would be very interesting for us to test different photoinitiators that we are currently developing on their cytotoxicology. Yeah.
Hi, I'm not sure if that was allowed join in live, but thanks for the answer. It's Jack here from the Dublin. Yeah, I was interested in biomaterials. We're working on a large number of various hydrogels and looking at the new crosslinker. I was just wondering how that will impact that. Also, if I can, thanks Grzegorz for inviting me, by the way. He's somewhere in the background. You mentioned nanoparticles. We're working here on a lot of nanoparticle based hydrogels inside, and I wonder how the transmission problem can be solved with, well, basically absorbance of nanoparticles with the need of transparency in your system.
Yeah, this is always a problem. Actually, you can try to make one of these solutions, put it in a cuvette, and look on the spectrophotometer what the absorbance is and how much light is transmitted at 405 nanometers. And then you see. So when we are talking about small build rooms, there is a certain tolerance towards lower transmission, but for optimal results, we really need high transmission. I actually don't know what nanoparticles or particles you're talking about.
Lots of magnetic stuff, so they are very brown at the concentrations we need them to work, or black. We also have some gold nanoparticles, but again, not that much. But still, there will be some issues. I guess you'll have to come up with some clever chemistry of embedding them at concentrations that would still yield a response.
Yeah.
Well, sounds interesting.
In the end,
Stay in touch.
Yeah. Actually, if you want to, I think my email address is also shared anywhere, so you can always get in touch to us. And we are really happy to stay in touch and go into detail with some particular problems. That
sounds brilliant. Thanks. I'll leave it back to Anna. Sorry for jumping in. Thanks.
No, thank you.
It's okay. So maybe next question. I'd like to know more about the cost of purchase for machine and materials. Also, if you plan to make a machine with larger build volume, say 300 meter cube.
Yeah, good question. So together with Sygnis, we are offering the prototype for 60,000 euros in the basic version. You have to keep in mind that it's only a limited number of prototypes that we are selling. And but there are also some possibilities of individualization. So in the end, we will sit together with you and really define your needs. And then we will see, but this is more or less the price range. Right now we are offering the Xolo with a build volume of 50 times 70 times 90 millimeters. This is more or less oriented on the need of the dental field, because like a mouth is really fitting in there for a dental model. What do I read there? A build volume of 300 millimeters cube. When you remember again our coordinate system X, Y, Z, I think in Y and Z we don't have much limitations. So in Y it's the height of the light sheet. This is just a game of intensity of the laser. This can be solved. Then in Z it's how long the print axis is actually moving. This is also no issue, but as already mentioned in the question before, we have one issue with the penetration depths along the light sheet, because there the photoinitiator has to absorb, and it has to absorb homogeneously, and there we're fighting against Lambert-Burr's law. So right now we set this to 50 millimeters because there it's working really nice and smoothly. The maximum we were printing so far was 100 millimeters, but right now we don't recommend on it. For that we need to develop a new like iteration of photoinitiators that have a better what is it? Separation of the bands. Yeah, contrast. We call it internally. We call it contrast. Yeah. So much about the build volume.
Okay. The next one. Could you tell us if the printed elements could be processed thermally, bending or pressing without losing its properties? And do you know what is the attention or absorption coefficient? It's the question from Jarosław.
Okay, I'm trying to digest. Processed thermally without losing its properties. Is it a question whether they are like HDT materials, high deflection temperature materials? I don't know. Actually, it's
Hello. I mean, could you, for example, draw it into a fiber from it? Like, for example, you have the plastic fibers, and so here I'm wondering if you could simply print some element and then heat it and make a thinner element piece of it. So it's
so like printing a pre-object and then thermally processing it to make it even thinner. Or actually, if you have such a material in hand that is an acrylate, then it should be possible. But usually we are having highly cross-linked networks, and I don't know whether they are like thermoplastic materials still. It's really depending on the material that we are using.
Okay, but still
maybe this could be a nice thing to investigate in the future.
Okay, thanks for the answer. And about the attenuation, because you mentioned that you would like to make a lens by this technique. So my question is, what is comparison between the attenuation optical is how much you lose, how much light you lose when the light is passing through this, for example, 1 centimeter piece.
So what is the transmission of the materials for optical applications? Yeah, I can't give you a value. Did we measure this? We didn't measure it so far because, frankly speaking, we are still optimizing the post-processing to have low yellowing and so on and so forth. So we are. I think we have shown very clear objects already. It will be depending on the wavelengths actually. So. I'm sorry, I can't give you a very clear answer, but from the eye, they are quite transparent in the visible region.
I think you can make things for UV optics, but for the visible, it should be okay.
Okay, thanks for the answer.
Okay, so I don't see any more questions, but maybe you will share your email on the chat. So if anyone has more specialistic questions, and I will share your page after that. And I think we're about to finish our webinar. So I want to thank everyone be here in our first webinar from the series. Thank you guys. That was an awesome presentation. I didn't expect to get into the machine, so that was great. Great invention. And so yeah, I think everyone who has more specialistic questions, they can ask you directly. I'm sharing your page on the chat, and I want to also invite everyone to visit also our pages and webinars we have prepared. The next one will be at 12, and yeah, it will be about. Okay, so sorry. Feel free to visit our page. We prepared webinars for every month will be the new series on the different theme. Just check the page and register via mail. So thank you so much, and have a nice day. And I think we can finish from them.
Yeah, thank you very much for giving us the opportunity to present today, and also from our side for everybody. Have a good day, and don't hesitate contacting us. Bye.
Ciao.